Okay, this is the second hour of Physics 1A for May 24th, and we're now going to talk about Kepler's second law, which is about the motion of these planets. So to describe this law, I'm again going to have to draw a picture of an ellipse. So we start off with an ellipse. We'll draw one line through it so we can... So if this is the center, and this is the focus, so here's the sun sitting at one of the foci of the ellipse. And then up here we'll put a planet. And what we're going to say is, suppose that this planet, which we'll label as P, moves in this direction to some new position here. So we'll call that point P prime. So this is just the planet at one point in time, the planet at another point in time. Kepler's second law says that if you draw a line out to where that planet is, from here to here, and actually, we're going to draw a vector, I think. I don't want to shape. We'll draw a vector. So if I draw a line from S to P, and then I draw another line from S to P prime, okay, and actually I'm going to have to draw one more line now that I think about it. At least one more. I probably have to draw several more. So let's just draw a few of these. Trying to be as accurate as I can with this here. It's not super easy. Okay, so this is what Kepler's second law says. It says that if I draw a line from the focus or the sun to the planet, and I look at how that line moves over time, then I can say that there's an area that's made right here, kind of a curvilinear area, where you have almost like a triangle where one side is just this curved path right here. What Kepler's second law says is that if you make sure that you draw equal areas every time here, so what I tried to do was I tried to basically make it so that the areas kind of got skinnier and skinnier. I didn't do a great job, but you can probably tell that this last area here has a really skinny angle right here compared to the first one that I drew, which has a kind of bigger angle right here. The idea is that if each of the time intervals between these points is the same, so if each of these points represents where the planet is, and every one of them has the same time interval, so this, let's say, is delta t, this is the same delta t, this is the same delta t. In fact, we could pick a number, like let's say delta t was equal to 1 month in each one of these cases, okay? So same time. Kepler's second law basically says this. It says that the line drawn from the sun to a planet will sweep out equal areas in equal times. Equal areas in equal times. Okay? So if this represents a month to go from here to here, it'll take a month to go from here to here, as long as the areas of those two segments, this area here, is the same as this area right here. Okay? Does that make sense? That's how he described what these planets are doing, is to say that those areas will be constant. Okay? Now, this has some effects that are, I don't know, probably something that you may have learned before. I don't know. Let's see. So let's draw a bigger version of this, and let's be kind of a little more extreme with how we draw these shapes. So suppose I take my object, and there it is, and I have my sun right here. Now, what I want to do is to see when you have an extreme case where the sun is really far away from the center of your ellipse. Let me show you what you have to do to make this work. So we'll again draw lines here. So we'll have one line that goes like this. Now, we're going to do equal areas and equal times, and the next line we'll do is this one right here. So this is going to be my area. This is going to be my base unit for area right here. In fact, let's make it a little fatter so I don't have to draw so many lines. So this is my base unit for the area here, is this area between these points, okay? So if I want to make equal areas and equal times, then it's pretty obvious that if I take another line and make it have pretty much exactly the same angle right here, something like that, this is probably about the same area, right? Pretty much if that angle is the same as this angle, then these are the same area. Okay, so it looks like it's the same area, right? Okay, so we imagine a planet, and it's moving from here to here to here. That's where the planet is. And these areas have to be equal to each other, okay? So that implies there is a certain speed at which the planet goes by here, okay? And I'm going to mention something about orbits, which is, this is the sun, right? This point, which is the farthest point away from the sun, is called the Aphelion. Or in general, it's called the Apoapsis. Now, you've probably never heard these words before, unless you've taken an astronomy class, but you probably have heard the word apogee before, right? Has everyone heard the word apogee and perigee before? Apogee is the same thing for the Earth, okay? This point on the opposite side over here is called the Perihelion. Perihelion, or the Periapsis. For an orbit, these are the far point and the near point of the orbit, okay? This is the far point. And this means basically near point. This is the distance of closest approach. This is the distance that the planet is the farthest away, right? Okay, so if I want to do the exact same thing, if I want to have a similar sized area over here on this side, I would argue that I'm going to have to do something like this. And this might not even be enough. So in order to get a similar area on this side, I'm going to have much kind of like wider angles than I do over here. So I guess the first question to ask you is, do you think that this area here is the same as this area here? Or do you all think that in order to make this whole area inside of this little region right here bigger, do I need to make this even bigger here? What do you all think? Not sure. Maybe I didn't do it perfectly, but this one is wide enough that it's conceivable that this skinny area is pretty much the same as this wider area, right? Okay. So I said that over here, if we say that this is the velocity of the object when it's at apogee, let's call this one V sub A. Call this one VA. Okay. That it's going to have a velocity over here. And the thing is that it has to cover a lot more ground, because the idea is that each of these time intervals has to be the same. So if this is 1 month, then this has to be 1 month, and this has to be 1 month over here too. Each of these traversals from this point up to here has to be a month. From this point over here has to be a month. So you can see that once it gets to the periapsis side, the perihelion side, it has to be going a lot faster. So the velocity of the object at this point then is going to be really fast. We'll call this one VP. Okay. So one of the things we can say about this is that the velocity at the apoapsis has to be smaller than the velocity at the periapsis. This is going to be the place where it goes the fastest. So what this means is that if you're tracking what this planet is doing over time, it's going to basically be going very quickly around here, right? And then it'll go this way and it'll kind of slow down. It'll be going really slow when it gets to here, and then it'll start to pick up speed until it swingshots around this thing, and then it comes back and it goes slowly. So it goes slow when it's far away and fast when it's close. That is pretty much what Kepler's second law says. Because in order to make it so that the lines are equal areas and equal times, the only way to do that is to have it cover a larger distance when you get close to the sun over here. Because or it's cover a larger distance in a shorter amount of time, which is going to mean a larger velocity. So that's pretty much what Kepler's second law says. Things go really fast when they're close and really slow when they're far away. That's pretty much it. Does that make sense? How that would fall out from this theory that the line drawn will sweep out equal areas in equal times? Does that make sense? Okay. All right, so the next thing we want to do is to take this idea and use more modern language that we've already learned to say something more concrete about these orbits, okay? And to do that, let me come back to my picture here. And let me get rid of these pieces that we don't need. Okay. All right. And maybe also let me move the second point a little over so that we can have some room to work with here. Okay, so we have this planet, and I drew these radius vectors here, and here. And we have our area vector right here. I'm going to say that the area that these things sweep out, so we're going from r to r prime. And I'm going to draw one more vector inside of here, which is going to be dr, and it's going to go from the original point to this point right here. And maybe I'll make it a different color, like green. So this is going to be dr, or delta r, whatever you want to call it. And the idea is going to be that we're going to make this kind of an infinitesimal change. So I'm also going to define the area here to be dA. And I'm going to put a vector symbol on there because you can. All right. So equal areas and equal times, right? So if I wanted to describe what that area is there, I would argue that I can say that the area inside of there, dA, would be equal to r cross dr. And to give you an understanding of why this is the case, I'm going to draw a parallelogram. This parallelogram, right? There we go. So this is just kind of an aside to describe why what I just wrote here is true, okay? So I give you a parallelogram, but I tell you that it's made up of a vector here that we call A and a vector here that we call B. Yeah, actually, this will be B. So there's vector B and there's vector A. This would also technically be B, and this would also technically be A. So we could write like this if we want to, okay? Oh, I left something out. We're going to have to divide this by 2. Sorry. Okay, now, how do I find the area of a parallelogram? How did you all learn to find the area of a parallelogram? Base times height, right? Okay, so we need to draw a height in here. So let's do that. The height of my parallelogram would be something like this. I can get a straight line in here. Something like that, right? Yep. And the next thing I'm going to do is I want to kind of, I just realized that it's going to be a lot simpler if I do something to change these just a little bit here. I'm going to change the direction of B to point to the left. I don't want to do that. Just going to get rid of that little thing. That's okay. So we're just going to make it so that B points left, actually. So our B vector is going to go, whoops, thought I clicked on that. Our B vector is actually going to point this way. So A is this way, and B is going to point this way. Okay, and then we're going to define this angle right here to be phi. And that's h. Okay, so if that angle is phi and this side is h, then would you all agree that h is equal to a times the sine of phi? Because, yeah, h opposite, right? And then to find the area, we would basically just be doing the length of A times the sine of theta, that's the height, multiplied by B, right? Or the other way we could have found the area, which would have given us the same answer, would have just been to do A cross B. And that would actually give us a vector direction for the area. Would you all agree that you get the same answer? If you do A cross B, you basically get A times B times the sine of phi. So it's the same thing, right? So in my picture over here, let's come back. I have what is a piece of a parallelogram made up by the vectors r and dr. And the area of that, the area of the parallelogram that they would create, like the parallelogram would go like this, right? The area of that parallelogram would be r cross dr. The area of the triangle, we have to divide by 2, right? So that's why I divided by 2. So that's my area then. We just do r cross dr, and we divide by 2, okay? Now, all we're really going to care about is the magnitude of this, so we'll just put absolute value symbols on here to say that we're only caring about the magnitude of these vectors. And for the dA on the left-hand side, what Kepler's second law says is the line drawn from the sun to a planet will sweep out equal areas at equal times. So what that means is that we need to divide both sides of this by some time interval. So I'm going to divide this by dt, and we'll divide this by dt as well. And the idea of what Kepler's second law says is that this quantity has to be a constant, right? dA dt, the rate at which the area is swept out, has to be a constant. The rate at which the area changes has to be a constant, okay? All right. So now, when we look at what we have on the right-hand side, we have r cross dr, and there's a dt that shows up in the denominator. That means we have a r cross dr dt, basically, right? And what's dr dt equal to? If r represents the position of my object, like the planet, relative to the sun, and then dr is the kind of change in its position, what would its velocity, right? So we can write this as r cross v now over 2 is now equal to our dA dt. The last thing that we're going to do is we're going to multiply both sides by mass. So we're going to put the mass of the planet right here. So I'll call that m sub p. And we'll multiply by the mass of the planet over here as well. And now we have, if I rearrange this, I can write it like this. I can write it as r cross m times v. But m times v is the same thing as momentum, right? So I can write this as r cross momentum. But r cross momentum is equal to what? This is what we learned about the last couple weeks, basically. mvr, what is that? Momentum times a distance. What is that equal to? We've been talking about it for like 2 weeks now. What is r cross p? P is momentum. If you take r cross momentum, what do you get? Angular momentum. That's right. So when we do r cross p, we get angular momentum. The symbol we've been using for that is L, right? So putting all of this together, what we have is that dA dt, we still have the mass that we multiply by both sides right here, is equal to r cross v mp. All of that is equal to L divided by 2. So we end up with a final result that says that dA dt is equal to the angular momentum of the planet, I'm just going to use the symbol L now, divided by 2 times the mass of the planet. And according to Kepler's law, this quantity has to be a constant, right? So That is what Kepler's law says in our modern language. It says that the rate at which the area changes is equal to the angular momentum of the planet divided by 2 times the mass of the planet, and this quantity is constant. Now, we're going to use this in a much simpler state, because if the mass of the planet isn't changing for any reason, then the angular momentum of the planet is the thing that's truly constant. So, the second version of the second law is just that angular momentum is conserved in planetary motion. L is constant. Angular momentum of a planet is constant. That's going to be something we can use to actually solve problems, basically. So all that discussion to describe what Kepler's law does to ultimately get to the idea that angular momentum has to be constant. Okay. Now, we probably could have figured this out if we knew how gravity worked, the force of gravity, but we haven't talked about that yet. So when we get to that, we can come back and describe exactly why this is true. All right. Does anyone remember, before we even do it, what was the condition you needed to have true in order for angular momentum to be constant? Conserved. Under what condition is angular momentum not conserved? What is the condition under which this is true in general? When is the angular momentum of a system conserved, and when is it not conserved? When the net torque is 0. That's right. Exactly. So we'll have to prove that there's no torque on the planet then, right? Because if there was a torque on the planet, then this wouldn't be true, right? So that's what we'll have to prove. But it's pretty easy to prove. That's the second law. Does anyone have any questions before we move on to the third law? So these last two are the main ones we're going to use for calculations, and we'll do some calculations with them immediately. Kepler's third law states that there is a relationship between the period of the planet, so I'm going to use this symbol to represent the period of the orbit of a planet. That is the time that it takes for the planet to get back to the same location, so it's the time for one orbit, right? So period means the time for one orbit, all right? And Kepler's third law relates this to the semi-major axis. So A is what we referred to as the semi-major axis. So Kepler's third law basically states this. Kepler noticed that if you look at, if you compare the semi-major axis to the period for each of the planets, so he had data for all the planets, right? Mercury, Venus, Earth, Mars, Jupiter, Saturn. He knew the periods. That was very easy to calculate. Just by astronomical observations, you can see how long it takes for the planet to kind of repeat its orbit. And semi-major axis was also something that was pretty well measured by them. So, putting these together, what he figured out was that if you take the semi-major axis cubed, that this is proportional to, I'll use this proportionality symbol, the period squared. Did I get that right? A cubed is proportional to period squared? Let me see real quick. Yeah, that's right. A cubed is proportional to the period squared. That's Kepler's third law. It's an actual. It's not an equation. It's basically a ratio. What this tells you is, for example, if I know what the semi-major axis for like Jupiter is, and I know what the semi-major axis for the Earth is, that if I take this and I cube these and do a ratio, that the ratio is going to be exactly the same as I get if I take the period of Jupiter squared and I divide by the period of Earth squared. That's what this relationship means if you don't understand the proportionality. Or another way to put it is that if I take a cubed and I divide by t squared, that this is going to be equal to a constant for all of the planets. Okay? As long as the thing at the center is... This is for everything that's orbiting the sun, basically. For all objects orbiting the same body, I guess what I'll say, because it doesn't have to be the sun. So Kepler's third law would give you the same answer for the ratio of a cubed over t squared for all of our planets. You get the exact same constant for all of them. We'll derive what that constant is here in a second. And if you did the same thing for all the moons of Jupiter, for example, all the moons of Jupiter, when you take their semi-major axis cubed over period squared, you also get a constant, but it would be a different constant, right? So you get a different constant for Jupiter and the things that orbit it. You get a different constant for the Earth and the things that orbit it, such as the moon and all of the man-made satellites that we have. You get a different answer if you put the center of the galaxy in here. And for the objects, you just had the center of the galaxy. At the center of our galaxy, there's a massive, supermassive black hole that holds together our entire galaxy. And Kepler's third law should technically also work on all of those stars. But what we're going to learn is there's some problems there that modern physics also is still trying to deal with. But that's Kepler's third law. It's a very good law. It's held us. It has worked for everything that we have found, mostly. Definitely within solar systems and stuff like that. Okay, so we're going to do a problem or two with these last two laws before we go into talking about gravity. Does anyone have any questions before we do that? So just to summarize what we just did, Kepler has three laws. The first law is planets orbit on ellipses. The second law is angular momentum is constant. And the third law is this relationship. Those are Kepler's laws for the orbits of the planets. In very many ways, these are a lot simpler than what came before them. Because to remind you what we said came before, Copernicus had to put a bunch of epicycles to make circular orbits and keep the sun at the center. And also Ptolemy had to have these complicated epicycles as well to describe his theory. And from all of that complication, we're now down to just three ideas. Elliptical orbits with constant angular momentum that obey this law. That's it. And that's what Kepler figured out. And that's, to this day, Kepler's laws are still used to describe planetary motion, the motion of orbits, and it's pretty powerful. It's pretty amazing to me to think that he could have figured all this out at the time that he was figuring it out. This must have been, he didn't have computers. This was, I want to say, it's like 14, 15, 1600s, something like that. So no access to computers. This all happened before the advent of calculus, so he didn't have calculus. All he had was just geometry, pretty much, to describe how this all worked. Okay, so let us look at some problems we can use Kepler's laws to solve. The first problem says the average distance between the Earth and the Sun is defined as 1 AU. Okay, so we're going to be using this unit a lot. The distance between the Earth and the Sun, so here's the Sun, here's the Earth. We call that distance 1 AU, 1 astronomical unit. And we can convert it to meters if we need to in other problems. So just to know what that is, 1 AU is equal to, I believe it's 1.5 times 10 to the 11 meters, I think. I'll look that up and check it if we have to actually use it, but I'm pretty sure that's what 1 AU is equal to. It's a very large distance. It's also equal to about 8 light minutes, which is the distance that light travels in a minute. So that means that it takes light about 8 minutes to get from the Sun to the Earth. Okay, so the average distance between the Earth and the Sun is 1 AU. The average distance between the Jupiter and the Sun is 5.2 AU. We want to find the period of Jupiter's orbit in years. So I'll just make a little picture right here. So it's saying if this is the Sun, and this distance is the distance from the Earth to the Sun, and then Jupiter is like way out here. Here's Jupiter. This distance is 5.2 AU. And this distance between the Sun and the Earth is 1 AU. We're going to use these as our semi-major axes. And we are going to calculate the period of Jupiter's orbit. So we want to find the period of Jupiter's orbit. Okay. around the sun. So for this, we are going to use this equation that I actually just wrote down here. So Kepler's third law says that this relationship should be true. If I take the semi-major axis of Jupiter cubed, divide by the semi-major axis for Earth cubed, it should be equal to the period of Jupiter squared over the period of the Earth squared. Okay? And we're trying to find this answer right here. Okay? So let's rearrange things a little bit. So if we take the semi-major axis of Jupiter cubed, divide by the semi-major axis for Earth cubed, and then we multiply by the period of Earth, TE, squared, that this should give us the period of Jupiter as long as we square root it. So we'll end up getting period of Earth times the square root of AJ over AE. This we have to cube, and then we square root it. That's going to be our answer. You don't have any questions about how we got to that answer? What am I going to use for the period of the Earth? What is the period of the Earth's orbit around the sun? How long does it take for the Earth to go around the sun one time? No. How long does it take the Earth to go around the sun? That's how long it takes for the Earth to spin once on its axis. How long does it take for the Earth to actually go around the sun one time? $365 days, give or take. Or just a year. How about we just choose 1 year? Because then we can get the answer in years. For these two, we're going to use the numbers that were given in our problem. So the square root of, for the semi-major axis for Jupiter, we're going to use 5.2 AU. Because we're doing a ratio, we don't need to change this to meters. We're going to divide by, so the distance between Earth and the Sun is 1 AU, so that's going to be what goes down here in the bottom, so divided by 1 AU. And then we need to cube this. Notice that our units will cancel out here. The astronomical units here cancel, and so our answer is going to be in years. So the answer here is going to be whatever 5.2 cubed square root is. I think the answer is something like 11 or 12 years. You guys calculate that and tell me what you get. What do y'all get if you calculate that? I got 11.9 as well. That means that it takes Jupiter 11.9 years to orbit the Earth, or sorry, to orbit the Sun one time. Okay. Anyone have any questions? Notice that in order to do this type of a calculation, all you need are reference distances. You don't need actual distances. So just to kind of emphasize the power of Kepler's third law, right? So what I said is that for all objects orbiting the same body, a cubed over t squared is a constant, right? So you can use the Earth as your measuring stick, basically, right? You can say, let's define a for the Earth to be 1 AU. And let's define the period for the Earth to be 1 year. In that case, what's the constant equal to? So if we plug in A is equal to 1 AU, and we plug in the period is equal to 1 year, we need to square this, and we need to cube this, but then our constant is basically just equal to 1. Right? And then, once I know that this is equal to 1, and I observe this, for example, the period of Jupiter, which again, like I told you, this is very easy to observe. It's really easy to notice, especially when you have lots and lots of free time. it's very easy to notice and figure out what the period of Jupiter is. You just need to observe it over a long period of time, and you'll figure out that this is what the answer is, right? You'll figure out that it takes about 12 years before Jupiter repeats its cycle, because the planets go in cycles, okay? So this number is very easy to figure out and was well known prior to his observations. So if you then want to figure out what the distance between the Sun and Jupiter is, which that's kind of an impressive thing to be able to state, that you can actually measure the distance from the Sun to Jupiter, because it's a massive distance that you can never measure with a ruler, right? But if you know this, and you know Kepler's law, you can immediately calculate that the distance between Jupiter and the Sun is 5.2 AU. 5.2 times as far away as the Earth is away from the Sun. And that's really powerful, right? It's really powerful to be able to measure astronomical distances that you could never measure with your eyes or with your hands or with a ruler or a tape measure, but you can find another way by using this relationship to actually find what those distances are. That's a really powerful thing to be able to do. It's a really powerful thing to be able to do. So, does anyone have any questions? Do we want to move on to another problem? Alright, so this is the second problem we want to do. This one says, Comet Norm orbits the Sun in 100 years. At its near point, it is traveling at 29 kilometers per second and just grazes the Earth's orbit. At its far point, we want to find A, its distance from the Sun, and B, its speed. So here's our orbit. We know there's a comet traveling on this orbit. We also know in order to have an orbit, you need to have something that is at the center that's doing the orbiting. So we need the Sun on our picture right here. So let's put in here, here's the Sun. And what we know is that comet Norm, so we'll just put an N for this comet right here, N. It says it orbits the Sun in 100 years, so that's its period, right? So the period for this comet, we'll call it T sub N, is equal to 100 years. It says at its near point, it is traveling at 29 kilometers per second and just grazes the Earth's orbit. So its velocity at this location, which I'm going to call, I think I'm just going to call it VP for the velocity at perigee. We know that this is equal to 29 kilometers per second. This is the closest approach. So when the comet gets to the farthest point, the apogee over here, its velocity is going to be much, much, much smaller. I'm not really drawing these properly to scale. But Kepler's second law told us that things will move fast when they're over here and slow when they're over here in order to conserve angular momentum. So this we'll call the velocity at Apoapsis, or Aphelion. And then there's our planet. We don't know what this is, but we want to figure this out. This is what Part B asks us to do. We want to find, at its far point, its distance from the Sun and its speed. So these are the things that we want to calculate. So I'm going to call this distance right here R sub P. I'm going to call this distance right here R sub A. Okay, so RA is going to go all the way from there to there. And RP is the remainder from here to here. And we know that it just grazes the Earth's orbit. It says at its near point, it's traveling at 29 kilometers per second, and it just grazes the Earth's orbit. So what that means is that R sub P, if it grazes the Earth's orbit, what would R sub P be? What would this distance be? If it just grazes the Earth's orbit, what does that mean? What does that mean? Got the Earth, it's orbiting the sun. What does it mean that this comet just grazes the orbit? What does that mean? RP equals 1 AU. Thank you, Joanne. That's right. Yeah, the idea is that our planet is, or our comet is basically coming in here, and it gets close, and then it kind of goes away like this, so that this distance right here is the same as 1 AU. Yeah. So R sub P then has to be equal to 1 AU. Okay. Does that make sense? Do you want to have any questions about that? All right, so what do we have? We have velocity at perigee, or at periapsis. We have the distance at that point, and we have a period. We know it's orbiting the sun, and our goal is to find this speed over here. So basically, part A of this question, we want to find what is R sub A equal to. And then part B of this question, we want to find what the velocity at that point is equal to. Those are the two things that we want to calculate. So what do you all think we should do? How should we figure this out? What kind of equations can we write down to relate the unknowns in this problem to the things that we do know? How do I know that RP is equal to 1 AU? Okay, I'll just explain that one more time. So suppose that I have the sun right here, and I have the Earth right here, right? And the Earth is orbiting on a circle, roughly we saw, close to a circle. It looks something like this, probably. So the Earth's orbiting around the sun, right? And we know that the distance between the Earth and the sun, the size of this orbit right here is 1 AU, right? 1 astronomical unit. It's our universal measuring stick. We use the distance between our star and our planet, and we call that 1 AU, right? It says that Comet Norm orbits the Earth in 100 years. At its near point, it is traveling at 29 kilometers per second. And so at its near point, it just grazes the Earth's orbit. So what that means is if we take our orbit for our comet right here, the orbit for the comet, in fact, I guess I could just copy it. Copy, paste. That's the orbit for our comet, right? And what we're saying is basically something like this happens. That the distance of the comet's approach just grazes the Earth's orbit. So grazes means it kind of comes in here and it just grazes the orbit and then it leaves, right? So that distance then has to be equal to 1 AU. Does that make sense, Chris? Okay, no problem. All right, so 100 years, 1 AU, all this information. So again, our goal now is to find its distance from the sun and its speed. How can we find either one? Whatever one you all want to do first, we can do either one. How could we start this? How would we start figuring this out? Sorry, I don't know if you all are hearing those sounds, but I guess I have to close this. Where do we go? What do I write down? What do I do next? What would you do next? Well, I'm gonna let you think about it. We should take a break now anyway, so we'll take a 10-minute break. Try to figure out